the amount of mass times the distance to the axis, which I'm saying is 2 feet, or x, right? Good. Now, now if I rotate it this way, all right, now it's rotating about an axis through my shoulder. Now, what is the distance from the weight to that axis with the length of my arm? So now its moment is the mass times the lever arm to the other axis, which in this case would be degree. So we're establishing that masses have moments, and the moment is the distance from the mass to the axis, or origin of coordinate. Now I want to describe something that you all know from real life experience. Suppose I now have here a 2-pound weight, and here I have a 1-pound weight. And here is my axis of rotation over here, so that this distance I'm going to call x2. It goes out to that one, and this distance I'm going to call x1. So let's just call this m1 and m2. What is the moment of m2? What is the moment of m1? m1, x1. Agreed? They both have moments. Now, I'm going to indicate that there's a special point in the middle, which is called the center of mass. And that special point in the middle has the property that if you put a fulcrum here, the two will balance, like a seesaw. That point is called xcm. It's the distance of the center of mass out from the axis, from the measuring point. Now, if this balances, then the amount of torque on this side is equal to the amount of torque on that side, agreed? And the torque is the weight times the lever arm. So this weight times this lever arm equals that weight times that lever arm, true? You know this from a seesaw. If this guy has half the weight of this guy, you put him twice as far away, and the seesaw works. We all know from personal experience. So I'm going to indicate that this distance here is xcm, x1 cm. It's the distance of x1 from the center of mass. Now this distance is the distance of x2 from the center of mass. Okay? Now I think you agree that m2 times x2 cm equals m1 times x1 cm for balance. The product of m2 times its distance equals the product of m1 times its distance for balance. We all agree to that? Well, let's show you a simple demonstration. Here I have an empty seesaw. I'm going to put 2 weights at a certain distance. Now, Stuart, for balance, where should I put the other weight? Half as far or twice as far? And we achieve balance. So this weight is twice as far as that one because it's only half as much. So this mass times this lever arm is equal to that mass times that lever arm. All right, we're going to record this for all posterity. So up close and all the rest. Okay, now I want to demonstrate something about one of the problems you're going to be working with. How do you find how far the center of mass is from the axis? How do you calculate how far the center of mass is from the axis? You use this principle right here. Notice that x1 cm equals xcm minus x1. Agree? This distance, it's this distance minus that distance. This distance is this distance minus that distance. All in favor? So this is yeah. This is x1 cm. x1 cm. Good. Now, what does x2 cm equal? It equals, let's see. Yeah?
XCM at the bottom is supposed to go only to the
Balance point.
balance point? Okay.
Yes. Okay. Now, x2 cm equals x2 minus x cm. Okay? This is x2 cm. So now let's rewrite this equation with these substitutions. We have m1 x1 cm equals m2 x2 cm. Now I can put these on the same side and say m1 x1 cm minus m2 x2 cm equals 0. Now let's make my substitutions. m1 times x cm minus x1 minus m2 x2 minus x cm equals 0. Let's continue to distribute these. m1 xcm minus m1 x1 minus m2 x2 minus m2 xcm equals 0. Now let's group some terms. m1 xcm, this is a plus sign, two minuses, plus m2 xcm minus m1 x1 minus m2 x2 equals 0. And now let's factor out an xcm, since that's what I'm trying to calculate. Now, so I'm going to put the minus signs on the other side again. We have xcm times m1 plus m2 equals m1 x1 plus m2 x2. Okay, so now solving for xcm, it equals m1 x1 plus m2 x2 over m1 plus m2. So just by doing a little bit of algebra, I'm able to, if you know the moments and the masses that are involved, then you can always find the center of mass. So let's point out what the center of mass is. Is this the moment of the first object? Is this the moment of the second object? Is this the sum of the masses? So x, center of mass, which the book calls x bar, is the sum of the moments over the sum of the masses. So let's touch base with the book. On 347, in the middle, x bar is equal to what? The sum of moments over the sum of the masses. Okay? A little bit of algebra, all coming from the fact that the center of mass is defined as the point where the balance occurs, where the torques are 0. And you can have any reference point that you want. And you can calculate the distance of the center of mass from that reference point. Now we did this for the x. And the same thing is true if we have more than two objects in our collection. The center of mass is the sum of the moments divided by the sum of the masses, if there's more than two or any other. And the center of mass is the distance, x bar is the distance of the center of mass from the axis, in the coordinate system. So of course it will change if you change the origin of your coordinate system. So now, you can also work with 2 dimensions at a time. So let's look at the diagram at the top of 348. So I invite you to come up and admire our high-priced Maryland demonstration equipment. So can we congregate up here a little bit and admire what we've got here? This is not easy to do. So please come up for a moment. Now, what we've established is that we have balance, and I'm calling this the x-axis. We now have balance in the x-axis, agreed? Now, I must also set objects so that we acquire balance in the y-axis. So if I set an object here, I must place this one so I achieve corresponding balance in both the x and the y-axis. So here I'm introducing a new moment about the x-axis, true? So this one must have the same moment about the x-axis. I'm also introducing a moment about the y-axis. So this one must also have the same moment about the y-axis, right? So I would suggest that we place them there. You know, it could be a bigger budget. And we achieve balance, true? Okay? So now we invite a participant to place 2 more objects in balancing positions. So, hi? He's gonna fail, I know. That's,
Sorry, this is your test. You have an hour and 15 minutes to figure it out. Oh, these are focused water.
hi. Very well done, sir. So now, if we say that this is one axis, now if I take this ruler, what is the moment of this object about the axis? It's its distance, agreed? To the axis. But what's its moment about this axis, going across this way, is its distance to that axis, true? So what is this object here? Its moment about this axis is its distance to that axis. What's its moment about this axis is its distance to that axis. So you see the objects have moments about both the x and the y, and the center of mass occurs when the sum of all of the x moments is 0. And the sum of all of the y moments is also 0. This designates this point. Now, this is not the origin of coordinates. The origin of coordinates can be down here, or it can be at the end of the table. And what you can generate from the formula is the distance from the origin of coordinates of that center of mass point. And that's, okay, the seats now. That's what we're going to do in this picture on page 348. In the middle of the page, we have an object that sort of looks like this. Right? Now, if we have a center of coordinates and an object that looks like this, someplace in that object is a center of mass. Now, the center of mass is known because it's the point that the thing will balance about, true? So all you have to do is yank it out of the book and put a chopstick under it, and you can find it. Or you can find it by integrals, because it's the point where the moments, internally come to 0, or it's given by the prescription outside. X equals the sum of the masses times their distance to the axis divided by the sum of the masses alone, and y bar is well, x bar would be, what would it be? What is, x bar is the location of the x center of mass. So the x center of mass is going to rotate about what axis?
Y.
The y, because I asked you, that's why, don't get smart. Okay, the y-axis. So the x center of mass is its distance to the y-axis. And the y center of mass, the moment of the y center of mass is going to be about what axis? About the x-axis. Now, since this is an irregular shaped strip, we can't just work like with two objects. If we had two objects, we would just take their distances, true? So what we do is break it into thin strips. Here is a strip.
How come Y isn't the sum of the mass?
It's at the sum of the.
It's a little faint. I'll make it darker so you can see it from back there. Now this strip has a mass, dm. And the mass of the dm depends on the area of the strip, because this is a very thin plate. Now this plate has a, what we call a two-dimensional distance, density, okay? Now since it's a thin plate, I'm going to say 1 square inch of the plate weighs 1 ounce, okay? 1 square inch of the plate weighs 1 ounce. Then how do you find out how much the whole plate weighs? You find its area, and you multiply by the density, or 1 ounce, true? So the area, the mass involved in this little strip is its density. In this case, it was 1 ounce per cubic centimeter. So this has what we call a two-dimensional density. In other words, the question is, how much mass is in 1 square unit of it? It's a two-dimensional density, because it's a two-dimensional object. And you multiply that by the area. And that's going to give you the amount of mass. Okay? So if we're looking for x bar, then it's the integral of the distance. Oh, it is x. I thought it was x. Yeah, we want the x location of the center of mass. It's about the y-axis, but its distance from the y-axis is x. Its lever arm is going to be x.
Does that change the Y?
Yeah, the other one will change also.
The book has center of mass x bar equals my over,
X bar.
equals my over m.
Repeat.
Center of mass x bar equals my over m.
Page.
348. And the moment is mx equals integral of y dm.
Because they're doing it in a more difficult manner than I'm doing it. I suggest that you follow the board on this. I followed their presentation, and they have an extra variable in there that is not standard. I've never seen it before. I'm not sure why they put it in there, and it doesn't add anything to doing it. So I suggest that we don't. And I didn't mean to mention that. I didn't know it came in so soon. So we can do it the standard way on the board and get to the same answer a little bit easier. So this strip is a distance x from the y-axis, true? So it has a moment x dm. And we have to divide by the sum of the masses, which in this case just becomes integral dm. So dm is given by rho dA. But the area that is encased by the red shading depends on the function of the object, because it has a value, a top value of y2 and a bottom value of y1. And those are given by the equation of the curve for this particular object. If you have a very simple case where you are rotating a half circle, or you're looking at a half circle, okay, then the equation for the top of the circle is y equals the square root of r squared minus x squared. And this particular little strip would have a lever arm of x. So its dA would be rho times y dx. So it would be the density times the square root of r squared minus x squared dx would be its dA. So the dA depends on the function under which you are trying to calculate the center of mass. So putting them into the equation, x bar equals the integral of x dm over the integral of dm. So it equals the integral of rho times r squared minus x squared dx over the integral of the whole object. Now how do you find the mass of the whole object? It's the integral of dm. All of the dm's, agreed? So it is equal to the integral of rho dA, all of the rho's, all of the dA's. So it's equal to the integral of rho dA. What I'd like you to notice is that for uniform flat plates, what happens to the rho in the top and the rho in the bottom? Because they're just constants, aren't they? They come out of the integral sign to the front. And since there's one on the top and one on the bottom, what can you do with them? They cancel out, agreed? So for uniform flat plates, the location of the center of the mass is only geometric. It doesn't matter the weight of the plate. It's a geometric result, sir.
So if you keep on doing that, dA, like previously you defined it as rho y dx. So the bottom would be rho y dx.
Yeah, we can take it one more step.
So wouldn't most of that cancel out?
dA, oh, this is dm. This rho should not be here for dA. If I went one step further to say dm, it would be there. So that was a slip. So this is the setup of the integral to find the location